We're going to go ahead and do this video here on traveling waves. And the first thing we need to do is define what a wave is, and the simplest definition that I know of is it's essentially just a transfer of energy without, do a little shorthand, without transferring matter or mass. Oh, why is that acting funny? Sorry. I should have that fixed now. Matter. Transferring matter or mass. Okay? And that definition should kind of make sense for you by the time we finish, but essentially energy is transferred through waves, but as it travels through what is called a medium, this is what a wave, this is the matter or substance or whatever it is that waves travel through. So essentially, this could be like air or a wall or something like that. That these waves are traveling through the ocean, some sort of fluid, something like that. As the waves travel through it, ultimately the matter, the particles that make up the medium, ultimately end up right back where they started once the wave has passed through. So there's no actual displacement of matter or mass, but energy is transferred through it. It's kind of like if you were at the ocean and you were watching, say, there were some ocean waves going and there was a piece of, seaweed or something floating there in the water, some seaweed. The seaweed would go up and down, right? Well, actually kind of make a circular path here for ocean waves, but it would move around, but ultimately end up right back where it started before the wave actually hit it. So the wave carries that energy with it, obviously, since there is movement of the particles and whatever's there. But ultimately, once the wave finishes passing by, everything goes back to where it was before. You could think of this as like a waving flag, right? You see waves on a flag, right? So you have a flag, and it'll, look something like this, kind of, like a wavy flag with, you know what I mean? Like, oops, that was a bad line. Wavy flag, and it'll have. Why did I do that? We're having all kinds of issues today, but you'll have a flag waving, so we can make this like the American flag or something, stars and our stripes and stuff. And as you see this go through, you see the flag waving like this. Ultimately, the flag, though, despite the waves going through it, the flag doesn't actually go anywhere. So just a couple examples of, you see the wave going through the flag as the wind blows it, or you see the seaweed, going up and down and forward and back and around. Really should have done that more as like a circular path as the wave travels through the ocean, but the seaweed really doesn't get closer to the shore. The thing that moves something further or closer to the shore is the currents, not the waves. If that does happen, if it's just waves and there's no current, then you just float the same distance and the waves wouldn't actually move you or the seaweed or whatever anywhere. Just like the flag doesn't actually go anywhere. Once the wind stops blowing, the flag is right where it was before the wind blew. Okay? So keep that in mind. We have two main types of waves we're interested in. There's more than just these two, usually just a combination of these two, but the first type is a transverse wave. This is the kind you're probably going to be most familiar with. In this kind of wave, the particles vibrate perpendicular to the direction of the wave, going over top of that. So essentially it's kind of going to look like this, like the ocean waves, but it's more like the wave in the flag or a piece of string. If I were to take a piece of string and just vibrate one end of it or something, then you would see a wave go through it, and it's going to look something like this, right, throughout time. where this would be our equilibrium that we talked about before. And remember, simple harmonic motion was very much related to this kind of wave. If I had something moving in simple harmonic and I pulled that piece of paper underneath it, we would get a wave. And this is what it is. If I look at, so say this is this is displacement from equilibrium, and then this is just how far you get away from the end of the string as you're shaking the end of this string. Each one of the little bits of string, so if we took like this little spot on the string here and we put a red dot on it, all you would see of that red dot is that it would just move straight up and down between the the max and the min displacements, the amplitude, from the up here positive amplitude to down here negative amplitude, and it would just go in simple harmonic motion. And the same would be true for any other particle we looked at on here. It would just move up and down in simple harmonic motion. And so this particle is moving up and down, this red dot would move up and down, but the wave itself would be traveling in this direction. This would go up and then it would go down and it'd go up, and if you watched it, it'd look like this little crest of a wave was traveling this way down, down the line, down the string as it went along, and that would be a transverse wave. The other kind of wave that we can have is a longitudinal wave. Longitudinal. So we had transverse, now we have longitudinal, and this is very similar to this definition. So it's particles vibrate, but this time it's parallel. I'm going to use my little parallel symbol. Parallel to the direction of the wave. I don't want to write all that out again. But it's the same definition. Particles vibrate perpendicular to the direction of wave here. Particles vibrate parallel to the direction of a wave. And so this would be more like something if I took a slinky and I bunched it up at one end, so we stretched a slinky out here. I bunched it up one end and let it go. And what you'd see, especially if I kept doing that, maybe I took this into the slinky, and instead of shaking the slinky up or down like that, I moved it forward and back like that, like just pushed and pulled on it. And so what would happen is you'd get like, a compressed part of the slinky, and then you'd get a stretched out part of the slinky, and then a compressed part of the slinky, and then a stretched out part of the slinky, and then a compressed part of the slinky, and then a stretched out part of the slinky. And it would look something like this, where what you have is the coils in the springs of the slinky would be vibrating this way. So if we took and painted a real red spot on one of the little coils of the slinky, we painted that, you would see it moving forward and backward in simple harmonic motion like this, and then you'd watch these coils, the coils themselves would then just, these bunched up parts of the coil would just move on down the line this way. So if you have a slinky, try that. Just lay it flat out on a table, kind of stretched out, and then push and pull one in real fast, and you'll see a bunch of little compressions travel down the wave and go out the other end, or down the slinky and go out the other end. And that would be a transverse wave. Okay? And so that's our two main types of waves we're going to focus on. Be sure to know how to separate them. Examples of this was, of course, like a string or a waving flag or something. This is longitudinal, so the compression of the coils in the slinky in this example. And another big example of this is sound. Sound is actually a longitudinal wave, and I'll talk to about that in just a little bit on the video. But it's a compressional type wave where it compresses like that as they vibrate like this. You can't do a transverse wave in air. But the particles can bounce back and forth, and so what you'd end up with something like for sound is you'd have an area of high density compressed particles all pushed together, and then it would go to kind of like low density, and then you'd have this area of high pressure again, and then it'd be like low pressure and high pressure again and low pressure again. And these low pressures kind of like are, if we look at the transverse wave, it's kind of like this, where we'd have like this high pressure, low pressure, high pressure, low pressure, high pressure, low pressure, like that. And the same thing here, we'd have like this high and low and high and low and high and low, just to kind of show you what it looks like compared to the transverse wave. It would look, it kind of coincides one to one with that, where this stretching is the trough and the compression, the high density compression is the crest. Okay. Next, a little bit of math for this. We need to talk about the wave equation, or how do waves actually move? How do we do some physics to decide how fast the waves are moving and things like that? We've already defined terms in the last video for frequency and period and stuff like that, and all of that still applies here. We still have an amplitude. We still have an amplitude here that's, this height here is the amplitude. We still have a wavelength and stuff like that. So we have this kind of stuff, or I guess we should define a wavelength. Maybe I think I might have talked about it a little bit before. But the wavelength, if you're on this, is going to be the distance, of course. Actually, I think I did define this. It's the time it takes for it to repeat itself. It could be from there to there, there to there. They should all be the same. That's the wavelength. From here, and remember not to here, because here it was going up and here it's going down, so the wavelength is from here to here. There it is again, lambda. And we have the frequency. We can't draw the frequency on this graph because, well, we just don't know how fast this wave is moving or anything like that. This is just about all the individual particles, and I'll talk more about graphing these in a minute. But basically we need our wave equation, and for that we can start with velocity equals distance over time. And since we're talking about waves and they're very closely related to the simple harmonic motion, they're going to have frequencies and periods and wavelengths too. And so if we look at this, we can say that the time that it takes for it to travel one wavelength, right? Wavelength is the amount of, is the distance like from here to here. So the time that it takes the wave to travel a distance of its own wavelength from here to here, that amount of time is the period, because that's how long it takes it to repeat itself. So velocity is then going to be the wavelength over the period, but we don't like to, it's kind of uncomfortable to have 1 over the period, and we remember from last time that 1 over the period is the frequency. So just frequency times wavelength. So our equation for waves, for the motion of waves, our little wave equation is frequency times wavelength. You're going to want to use this one to solve waves. You can do it with this. It's essentially the same thing. You could look at like a distance that a crest traveled in a certain amount of time, but on your exam and everything, they're going to want to see you use this version of it. But it is essentially the same thing. So you can get the same right answer doing that, but you're going to get more credit, and it's going to look better if you actually use this version of it here. Okay, so just velocity equals frequency times wavelength. Frequency is a 1 over a second. It's a hertz, so 1 over a second times a length in wavelength, so that's a meter per second. Even still works for our units. Okay, so how do we go about graphing these? Well, we have 2 main ways to graph. The first is like the picture I drew above. We can graph the whole wave, all the particles in the wave, where we start with some little origin like the end of the string where the wave starts, and then we end up with some sort of sine wave that looks like this, just like simple harmonic motion. It's still a sine wave. But this axis is how far we get away from the origin of the wave. This is the displacement from equilibrium x, so F equals kx. So this one is, from equilibrium, and this one over here is from the origin of the wave. Okay, and so all of this would be like the entire string mapped out. Every little point along the string we go through and map out. It's kind of like we have a string and we're waving it, and we took a quick photograph of it. And whatever the shape was there, this is what this graph shows us. We went through and then graphed out the position of everything. If we wanted to let this run through time, of course, the string, if you, instead of taking a picture, you took a bunch of pictures and you played it like a video, you would see this wave moving along, say moving in that direction and everything. But this is just like a still single photograph of the wave while it's in motion. Some of the things we can write on here, like I wrote above, just write them again real quick, is the amplitude. So again, that's the maximum displacement from equilibrium. So, the amplitude there, and it should go straight across. And the same thing down here, it would be the same amplitude down here, A, except I guess negative A on the graph side. So you know that's the amplitude as well. And then in here we can write in the wavelength. So we can write in wavelength, could go from here over to here, that's your wavelength, or here to here, that's your wavelength. And we can't write frequency in on this because again we don't know how this is evolving in time. So if we want to look at something like frequency, we can look at a different version of this graph. And instead what we're going to do is graph of, again, this will be x, and it's still from equilibrium, so it's still that same displacement from equilibrium, but what we're going to do is change, we're going to, come on, we're going to change this axis from distance from origin, we're going to change it to time. And so in this graph what we're going to do is look at one individual particle. So if you remember this picture up above where I said we put this little red dot on it and watch the red dot go up, what we're going to do essentially for this graph is instead of taking a picture of the whole wave, all the particles at once, and drawing that top graph, what we're going to do is just watch the motion of that single particle. And the graph is going to look very familiar, very similar. It's going to make a sine wave again. It's going to go up and down and up and down. But this one is through time, right? Not just a single picture of the entire wave of all the different particles, but one particle going up and down through time. This would be more the graph of as we had something moving in simple harmonic motion, we pulled the paper slowly underneath it and it drew out a sine wave. On this, because the vertical axis is still the same, we can still indicate and measure and read off of it the amplitude, right? So that's still the same. But if we read this length here, right? If we read from here over to here now, it's not going to be wavelength anymore because this is not a distance axis, it's a time axis. So if we read this length here, that's actually going to be the period. All right, it's the amount of time it takes for it to repeat. So that would be the period, that would be the period. They should all be the same. The period would be from here out to here. That would be the period because now this axis is time, so it's telling us time rather than distance. So this one up here, just to make sure we really understand and clarify this, this graph up here is all the particles. It's all the particles. It's the whole wave. All the particles. You know, the whole wave. Just a single picture of it. It's a snapshot. A snapshot. Oops. I don't want that. I don't want that there. That's not an in. A snapshot. Right? A quick picture of it. A snapshot of it. This down here is a single particle as the wave travels through it. So it's a single particle as the wave travels through it, and that single particle undergoing simple harmonic motion. So that's its connection to simple harmonic motion. And so you can kind of just see that in there as it you know, works out with the same equations and everything still works nicely. Okay, so you're going to have to be very careful to make sure you can tell the difference between these two graphs. Don't mix them up. Remember, with the one where this axis is distance from origin, you're reading a length off it, which would be wavelength, and where this one is time, you'd be reading a time off it, which is the period of the wave. All right. So a couple last things. Let's specify this down a little bit, or you know, give a couple little types of waves that you need to know about. The first is sound, which I said we'd come back and talk about. Sound is itself a longitudinal wave. It is. I have a tough time to think about spelling that one right. It's a longitudinal wave. It's like that picture I drew up there. You go between areas of high pressure and then areas of low pressure. It's this compressional wave as it goes through. It's not a transverse wave. You couldn't do a transverse wave in a fluid like that. So, or in air, you can't really do that. And then there are a couple things, of course, between the compression, the high compressions or the You have the compression areas, and then you have the low pressure areas that are called rarefaction, RAREFACTION, rarefaction. But the main things you really need to know about this is one, something you've heard in regards to sound is the term pitch, like in talking in music, and what that essentially means is, and what it's determined by in physics terms, is the frequency of the wave. The higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. And then the other thing you need to know is volume. Volume is essentially the amplitude. The larger the amplitude, the louder, the higher the volume of sound is. So that's what that one tells you. Next, after this, that's pretty much it for sound. Just a couple of, make sure you understand a little bit about that. We'll work some more on it later. Next is electromagnetic waves. So prior to electromagnetic waves, it was thought that all waves had to have a medium through which to travel through, and that was the waves we described above. They had that medium, some material for them to travel through, and here we don't have that anymore. And this was a great shock to everybody when it was discovered. It was thought that this traveled through something called the ether, but they couldn't find any evidence of it. And so this turns out to be something that it's a little different. What they did is they lumped all the other waves from above, the sound waves, the ocean waves, the waves in a string or in a flag or something like that. They lumped those all into what are called mechanical waves. So everything above we've talked about have been mechanical waves, and now we're getting into non-mechanical waves, and that's this kind of wave here. It's an electromagnetic wave. It doesn't have to actually have a medium through which to travel. And what makes this electromagnetic wave is pretty interesting. It was discovered by Maxwell's equations, found that the speed of a reaction between electric fields and magnetic fields. Well, basically, what happens is electric fields create magnetic fields, and so what you have is you'll have this electric field oscillating one way, and I'm going to do my best to kind of draw this 3D. Right, here's the overall progress of the wave, going down like this. And what that is this electric field that'll point in one direction, and the electric field strengthens, and this changing electric field then creates a perpendicular changing magnetic field that kind of goes out like this, that's perpendicular to it. Sorry, it's kind of hard to draw. But this changing electric field creates a changing magnetic field like that, and then the changing magnetic field creates a changing electric field, and then the changing electric field then creates a changing magnetic field, and so on and so forth like this. And they're at right angles to each other. They're at right angles to each other. I'm just going to finish drawing the rest of it. They're at right angles to each other in most situations, and I'm sure you can look up a quick picture of this that's going to be way better than what I'm drawing here. Look better than what I'm trying to draw here for you, but basically they're at right angles to each other. If we were looking at it straight on, the electric field would be oscillating this way, and the magnetic field, if it was coming like straight at us, would be oscillating this way. In most materials, in a vacuum it does that, and that's really all we're interested in is a vacuum. And so it would look something like this. It's an electromagnetic wave. This is essentially light. It's radio waves. It's all those kind of things. And you're going to need to know the basic spectrum of it, and I'll write it down for you in a few minutes. You don't have to know it in like this horribly great detail, but it's going to be beneficial to you for knowing this. So when they first tried to look for this, what they found was if you look at most waves, like say you're looking at a boat, right? And as a boat travels through water, so this is an above view of like the boat. There's a windshield on the boat. Here's the motor, okay? So we're looking at a top-down view of the boat. The waves coming off the back of the boat, if you look at them, they get spread way out. They're not real close to each other, but the waves coming off the front of the boat are all crammed together, right? And this is because this is the direction of the boat. And so the boat is going in the same direction as these waves, so these waves off the front appear to be slower, and it's that same kind of Doppler shifting effect. I guess we haven't talked too much about it except we did last year or so. But it crunches all the waves up because every time a new wave is created, the boat's further ahead it was than it created the last one. So it's kind of keeping up with these ones. But these waves coming off the back of the boat, they get spread way out, and because we're moving away from them. And so this same sort of thing was expected with light. We expected to see the waves as Earth traveled around the sun. We expected the light waves going out in the direction we were going to be slower than the ones that were going out in the opposite direction we're going. So like if we had the sun here, right? If we had our sun here and here was Earth, as Earth was going around in orbit this way, we thought, well, if we point our little light in this direction, we're going to get a lower speed than if we point it out in this direction where we're moving away from the light. And it was actually a great failure of this experiment, big failure of physics, was that it didn't happen. It was found that no matter what direction they pointed the light, it always went at the same speed, and so it was kind of a big problem. And it was Einstein that came along, him and Lorentz, using Lorentz transformations to actually fix that. And what we found is that we have something called the universal constant, the speed of light. We make it with a little lowercase c, and it is about 186,282 miles per second. So that's about 7 times around Earth in 1 second, like 8 minutes to get the 93 million miles to the sun. And in SI units, it's about 3, or sometimes you see it as 2.99, but it's about 3 times 10 to the 8th meters per second. So it's very, very fast speed. And no matter how you're moving, no matter what you do, this is always measured to be the same, the speed of light in a vacuum. We haven't been able to ever change this. No matter how you're moving, it always turns out to be the same, and that's one of the things that's tackled in special relativity. Okay, next couple little things about regular terms you hear about light that you need to have the more scientific the scientific vocabulary for. First off is brightness, and brightness would be amplitude. So, however, that's a T. However bright the light is, that's based on the amplitude of the electromagnetic wave. And then color. Color is frequency or wavelength. Frequency / wavelength kind of thing. Like pitch above was the frequency wavelength. Here it's color. So the higher the frequency, the more towards the blue end of the spectrum it goes, and the lower the frequency, the more towards the red end of light it goes. So red light is a lower energy, a lower frequency, longer wavelength than blue light is. Blue light's a higher energy, higher frequency, shorter wavelength. So, you'd have something like a red light doing something like this, and then you would have, blue light looking something more like a higher frequency version like that, with a shorter wavelength, therefore a higher frequency, and this has a longer wavelength with a lower frequency, and they're both traveling at this same speed, 3 times 8 times 10 to the, or 3 times 10 to the 8th meters per second there. Okay? And if you notice the way I drew this, if you look at just one of these, then this electromagnetic wave is, I'm going to write transverse, and then I'm going to put like a little ish after it, transverse-ish, because technically it has no size to it here. It's just looking at the direction the electric fields are pointed. So it's kind of transverse, but the big kind of deceptive thing about this picture is it makes you think that light actually has like a height and a width to it, when it really doesn't. The length of these arrows drawn here just represents the strength of the electric field, not actually how long the electric field is. So just be kind of careful with that. You're going to want to say it's transverse, but just kind of remember it isn't actually like a physically transverse type wave. Okay. Let me go ahead and write down this basic spectrum for you. The longest wavelengths are radio, and you're going to be anywhere from the meter range, so like a 10 to the 0 up to bigger than that, usually around 10 to the second, but I guess on out to infinity, longer and longer. After that is microwaves. This is what you listen to the radio with and talk over radios with. This is what your cell phones work on and what you use to cook food in the microwave. It heats up water vibrates really well with the water molecules. And the range of this is 10 to the negative 1 times, or to 10 to the negative 3, and this is in meters. Right, so this is their lengths, their wavelengths in meters. After that, you have infrared IR, which you're used to, and it's going to be on the 10 to the negative 4th to 10 to the negative 6 type range. Then we have a small little part of the spectrum, which is the visible light. Visible light, and this is on the 10 to the negative 7th type range of meters, kind of around the hundreds of microns type meter things here. Then you have ultraviolet, and I'm going to explain the name infrared and ultraviolet in a second, but it's 10 to the negative 8th to 10 to the negative 9th. Okay, and that's it on its size scale. We have X-rays, named because when they were discovered, he didn't know what to call them, so he used the variable X, and they just stuck. It's X waves. This goes from 10 to the negative 10th to 10 to the negative 11th in range. And then we have the big bad ones, the ones that like come with radioactive decay, the really high energy bad ones that give you radiation poisoning and create the Incredible Hulk and that stuff. This is 10 to the negative 12th to 10 to the negative 13th, and I guess anything up beyond that is still maybe gamma range. But I guess if we get much higher than that, maybe if it starts becoming common, they'd give it a name or something. But I think that just goes on out forever. So that's gamma rays. This is called ultraviolet because if you look at the spectrum, it goes red, orange, yellow, blue, green, indigo, violet, and then ultraviolet is one step up higher than violet. Infrared is one step below red because again it starts with red, orange, yellow, right? It's the red and then orange and then going through the rainbow, right? Red, orange, yellow, and so getting higher and higher energies: red, orange, yellow, green, blue, basically indigo, and kind of violet gets to be like the purpley range. So it does something like that. Roy G. Biv, if you remember it. So this violet out here is for that, and this red infrared is right below red. That's where those kind of names come from. And then with sounds, you can have like ultrasonic, which is right above what we can hear, and infrasonic, which is right below what we can hear. So that kind of thing. But you need to know this basic ordering and these approximate sizes. You might be able to look up one that has a little more accurate. If you're more interested and you want to know it to like a deeper level, you can get it down to like, down to the, a lot more than just the order of magnitude of these. You can look one up, but I don't think you're going to have to know it that kind of level. You just need to know this basic order and the basic range of their wavelengths, just to the order of magnitude. Okay, I think that's pretty much everything.